Hello, my name is Shimon and I'm writing my bachelor thesis in physics at the Humboldt-Universität of Berlin. I am working on material fingerprints to determine the similarity between different materials based on their electronic density of states. In our poster, we will introduce you to the NOMAD Encyclopedia and show how it can be used to explore the properties of materials in the NOMAD data collection. The availability of large amounts of fair data is crucial in gaining knowledge and paves the way for big data-oriented material science. The NOMAD Encyclopedia supports this paradigm by providing the users with an interface that does not rely on expert knowledge in computational material science.
Hello, I'm Martin and I'm a PhD student at the Humboldt-Universität zu Berlin and I work on the characterization of materials based on similarity measures. For this task, having an accessible and normalized data source like the NOMAD Encyclopedia is a great opportunity for the discovery of structure and patterns in materials data. Next, I will give you a short tour through the NOMAD Encyclopedia.
You can start searching the NOMAD Encyclopedia by selecting an element from the periodic table. In this example, we choose silicon. Next, we click on the Properties button to select that we are searching for silicon in the diamond structure. Because we want to take a look at the electronic structure of silicon, we want that our results contain the band structure. Furthermore, we want to find calculations that use the generalized gradient approximation for the exchange correlation functional. Now that we have specified our search, we can click the Search button. We see the overview page of this encyclopedia entry. It consists of different sections. We can expand each section by clicking on the plus button. Here you can see the structure page of silicon. It contains the structure viewer where you can inspect, rotate and zoom the structure, as well as an interactive list that shows all the calculations associated with this material. The entries are grouped by exchange correlation functional and by the code that was used for the simulation. Here we can see a set of calculations that was grouped together to show for which unit cell volume the energy of the structure is minimized. You can select each individual calculation to see its properties. In the summary section, you can see the mean, the minimum and the maximum values for the properties of the calculations selected in the list above. Next, we take a look at the electronic structure page. You can select a calculation in the list on the left to show its band structure and density of states. You can move and zoom them to inspect the full energy range. In the Brilliant Zone viewer below, you can see the Brilliant Zone and the k-path that were used for the band structure calculations. Next, we are going to inspect the vibrational and thermal properties of silicon. Here you can see the phonon dispersion relation, the phonon density of states, the specific heat and the Helmholtz free energy. In the methodology section, you can see the type of calculation, the exchange correlation functional, the simulation code, the potential, and the basis set for each calculation of this material. You can filter this list by different criteria. The latest addition to the NOMAD Encyclopedia is the Similar Materials button. It allows users to find materials that have similar electronic density of states in the upper valence region. In our example, we can see that the material that is most similar to silicon is germanium in the same crystal structure, which confirms, in this case, our physical intuition.
In our poster you can learn more about the NOMAD Encyclopedia and how we found similar materials based on the electronic density of states. We thank you for your attention and we will be happy to answer your questions.